Welcome! Today, we will explore an interesting problem from LeetCode, problem number 390 titled Elimination Game. We'll break down the problem, analyze different approaches, and discuss their complexities. Let's dive in. In this problem, we start with an integer n, which represents the number of elements in a list. The list initially contains all integers from 1 to n in ascending order. The challenge is to repeatedly perform an elimination process until only one number remains in the list. The process begins by removing every second element from the list, starting from the leftmost element in the first pass. After completing this pass, the direction of elimination reverses. In the next pass, we start from the rightmost element and again remove every second element. This alternating pattern of elimination, left to right and then right to left, continues until we are left with just one number. The task is to determine and return this last remaining number. The input is an integer n where n ranges from 1 to 10 to the power of 9, and the output is a single integer representing the last number left in the list. Let's explore some examples to better understand the problem. In the first example, the input n is 9. This means the initial list is 1, 2, 3, 4, 5, 6, 7, 8, 9. During the first pass, we eliminate every second number from left to right. This leaves us with 2, 4, 6, 8. In the second pass, we reverse the direction and eliminate every second number starting from the right. Now, the list is reduced to 2, 6. In the third pass, we return to the left to right direction and eliminate every second number again. Finally, we are left with just one number, 6, which is the output. In another example, if n is 1, the initial list contains only one element, 1. Since there's nothing to eliminate, the last remaining number is simply 1. Now, let's look at another example where n is 6. The initial list in this case is 1, 2, 3, 4, 5, 6. In the first pass, we remove every second number from left to right, resulting in the list 2, 4, 6. In the second pass, we switch directions and eliminate every second number starting from the right. This reduces the list to 4. At this point, there's only one number left, so the output is 4. This example illustrates how the alternating elimination process works for a smaller input size. Finally, let's consider some constraints and edge cases for this problem. The input n can range from 1 to 10 to the power of 9, which means the solution needs to be highly efficient. For example, when n is 1, the list contains a single element, so no elimination occurs, and the output is simply 1. When n is 2, the list is 1, 2. After the first pass, only 2 remains, which is the output. For large values of n, such as 10 to the power of 9, it's critical to avoid simulating the entire list directly due to memory and computation limitations. The solution must use a more efficient approach to determine the last remaining number without explicitly constructing or iterating over such a massive list. To approach this problem, one way to think about it is through a simulation-based brute force method. Here, we simulate the process of eliminating numbers by maintaining a list of integers from 1 to n. The elimination happens in alternating directions, left to right on one pass, and then right to left on the next. To carry this out, you start with the full list, iterate through it on each pass, and remove elements based on the direction of traversal. After completing a pass, you reverse the direction and repeat until only one number remains in the list. However, this approach, while intuitive, is computationally expensive. Each pass involves iterating over the current list, which initially takes n time, and since the list size decreases linearly, the total time complexity ends up being n squared. Additionally, storing the list itself requires n space. This makes the brute force approach impractical for large values of n, such as n greater than 10,000, because the simulation becomes prohibitively slow and memory intensive. A more efficient solution lies in an optimized approach that avoids direct simulation by using mathematical reduction. Instead of explicitly maintaining and iterating over the list, we analyze the elimination process to find patterns in the indices of the remaining elements. For example, in the first pass, all numbers at odd indices are eliminated, while in the second pass, elimination alternates based on the new list structure. Crucially, the starting number, step size, and direction follow deterministic rules. After a left-to-right pass, the first remaining number increases by the current step size. For a right-to-left pass, this increase happens only if the number of remaining elements is odd. By leveraging these patterns, we can directly compute the last remaining number without ever constructing the full list. This is done by initializing variables for the starting number, step size, and direction, and updating them iteratively until only one number remains. This approach is not only elegant but also avoids the inefficiencies of brute force simulation. The mathematical reduction approach is highly efficient in terms of both time and space complexity. The time complexity is O log n, as the number of iterations is determined by the number of times n can be halved, which corresponds to the elimination rounds. Space complexity is reduced to O(1), since no extra data structures are needed, the computation involves only a few variables. This efficiency makes the approach scalable, even for very large inputs such as n equaling 10 to the power of 9. By avoiding the overhead of simulating the elimination process, this method provides a solution that is both computationally and memory efficient, which is critical for handling large-scale problems effectively. The mathematical reduction approach is the clear choice for solving this problem due to its superior efficiency. It capitalizes on the predictable patterns in the elimination process, making it both time and space efficient. For large values of n, the logarithmic time complexity ensures that the solution remains practical and performant. While the brute force approach is easier to conceptualize and implement, it is computationally prohibitive for large inputs. On the other hand, the optimized approach does require a deeper understanding of the elimination patterns, which might not be immediately apparent. However, once these patterns are understood, the solution is elegant, fast, and scalable, making it the most effective way to tackle this problem comprehensively. To approach the elimination game problem, we first consider a brute force solution that simulates the elimination process step by step. The algorithm begins by initializing a sequence, which is simply the input list of numbers ranging from 1 to n. Alongside this, we define a Boolean variable called left_to_right to track the direction of traversal during elimination. Initially, this flag is set to true, indicating that the first pass will eliminate elements from left to right. The sequence is iteratively processed using a while loop, which continues until only one element remains in the list. This setup lays the groundwork for simulating the rules of elimination specified in the problem, ensuring that every step adheres to the alternating traversal directions and elimination patterns required by the problem statement. The core of the algorithm lies in processing the current sequence based on the direction indicated by the left_to_right flag. For a left-to-right pass, we traverse the sequence starting from index 0 and remove every second element. This can be implemented efficiently by creating a new list that includes only elements at even indices. On the other hand, for a right-to-left pass, we traverse the sequence in reverse order, removing every second element from the right. This is accomplished by reversing the list, applying the same logic as in the left-to-right pass, and then reversing it back to maintain the original order. After processing the sequence, the direction of traversal is toggled by flipping the left_to_right flag. This ensures that subsequent passes alternate directions, as required by the problem. The while loop continues this process until the sequence is reduced to just one element. Once the iteration is complete, the last remaining element in the sequence is returned as the result. This element represents the survivor of the elimination game. By directly simulating the elimination process, this approach provides a clear and intuitive implementation of the problem's rules. Additionally, the alternation of directions is seamlessly handled by toggling the Boolean flag, ensuring that each pass adheres to the specified elimination order. It's important to consider edge cases while implementing this algorithm. For example, if the input list is empty, the function should handle this gracefully by verifying the input before proceeding. Similarly, if the input contains only a single element, the loop will terminate immediately, returning that element as the result without any further processing. These considerations ensure the robustness and correctness of the solution. To implement this solution, we primarily rely on two data structures. The first is the list ARR, which stores the sequence of numbers being processed. Lists are particularly suited for this task because they allow dynamic resizing and provide efficient access to elements by index. The second is the Boolean variable left_to_right, which tracks the direction of traversal during each pass. Together, these structures enable the simulation of the elimination process. In terms of complexity, the time required for the algorithm is proportional to the sum of the sequence sizes across all iterations. Since roughly half the elements are removed in each pass, the total number of operations forms a geometric series, n plus n/2 plus n/4, and so on, summing up to O(n). The space complexity is also O(n), as the list ARR is used to store the sequence. No additional data structures are required beyond this. The brute force simulation can be optimized in several ways. Instead of explicitly removing elements from the list, which can be computationally expensive, we can use slicing or a generator to reduce overhead. This avoids unnecessary copying of the list and speeds up the process. Additionally, mathematical insights can sometimes eliminate the need for alternating passes altogether. For example, by analyzing the pattern of eliminations, it may be possible to derive a direct formula for the result. Such optimizations not only improve the algorithm's efficiency but also reduce its complexity, making it more suitable for large input sizes. Exploring these alternatives can lead to a more elegant and scalable solution for the problem. This solution efficiently solves the elimination game problem using a mathematical approach rather than simulating the elimination process. The algorithm's key idea is to track the first remaining element, head, at each round and update it based on the direction of traversal and the step size. Initially, we start with head equals 1, which represents the first element of the sequence. The variable step tracks the distance between consecutive surviving elements, starting at 1 and doubling after each round. The remaining variable keeps count of how many elements are still in the sequence, and left_to_right toggles the direction of traversal at each step. In each iteration of the while loop, the algorithm determines whether the head needs to be updated. If the direction is left to right, or if the count of remaining elements is odd, the head is incremented by the current step. This accounts for the removal of elements at the current step. Next, the step is doubled to reflect the increased distance between surviving elements, and the remaining count is halved since half of the elements are removed in each round. The direction is toggled for the next iteration. The loop continues until only one element remains, remaining 1. Finally, the head represents the last remaining element, which is returned as the result. This approach eliminates the need to explicitly simulate the sequence, achieving an efficient solution with logarithmic time complexity, O log n. This is the Java implementation for LeetCode problem number 390, Elimination Game. The logic mirrors the provided Python solution, with type declarations and Java-specific conventions. The variables track the direction, remaining numbers, step size, and current head. The loop continues until only one number remains. The key difference is the explicit need for type declarations and syntax differences between Python and Java. To solve this problem, let's consider an example where n equals 9. Initially, we have 9 elements in the sequence. The number of elements remaining is also 9, the step size between consecutive elements is 1, and the first element in the current sequence is 1. We start by eliminating numbers from left to right. In the first iteration, since we're moving left to right, the first element that survives is updated by adding the step size to the current head. This makes the new head equal to 1 plus 1, which is 2. The step size is then doubled to 2, the number of remaining elements is halved to 4, and the direction of elimination switches to right to left. In the second iteration, elimination happens from right to left. Since the number of remaining elements is even, the head does not change and remains at 2. The step size is doubled again, becoming 4, and the number of remaining elements is halved to 2. The direction switches back to left to right. In the third iteration, we eliminate from left to right again. The head is incremented by the step size, so the new head becomes 2 plus 4, which is 6. The step size doubles to 8, and the number of remaining elements is halved to 1. At this point, the loop ends because only one element remains. The final state shows that the last remaining number is 6. Now let's look at another example where n equals 6. Initially, there are 6 elements, so the number of remaining is 6, the step size is 1, and the first element is 1. The elimination begins from left to right. In the first iteration, we increment the head by the step size, so the new head becomes 1 plus 1, which is 2. The step size doubles to 2, the number of remaining elements is halved to 3, and the direction switches to right to left. In the second iteration, elimination occurs from right to left. Since the number of remaining elements is odd, the head is incremented by the step size. This makes the new head equal to 2 plus 2, which is 4. The step size is doubled again to 4, and the number of remaining elements is halved to 1. At this point, the loop ends, as there is only one element left. The final state shows that the last remaining number is 4. Finally, let's consider the simplest case where n equals 1. Here, there is only one element in the sequence, so the number of remaining elements is already 1. The step size is 1, and the first element is 1. Since the number of remaining elements is 1, the loop does not execute. The last remaining number is simply the head, which is 1. To analyze the time complexity of the solution for the elimination game, we start by examining the number of iterations in the loop. The variable remaining initially equals n, and in every iteration, it is halved. This process continues until remaining becomes 1. The number of times we can divide n by 2 until reaching 1 is mathematically equivalent to log base 2 of n, or log 2, n. This gives us O, log n, iterations. Within each iteration, the operations such as updating the head, doubling the step, and having remaining are all constant time operations. Each of these computations takes O1 time, and since there are no nested loops or recursive calls, the total time for one iteration is simply O1. Combining these observations, we find that the total time complexity is determined by O log n iterations, each taking O1 time. Therefore, the overall time complexity of the algorithm is O log n. Now, let's evaluate the space complexity of the solution. The algorithm uses only a few variables throughout its execution, left to right, remaining, step, and head. Each of these variables occupies a fixed amount of space, regardless of the input size n. This means that the memory usage for variables is O1. Additionally, the solution does not rely on any auxiliary data structures like arrays, lists, or recursion stacks, which would increase space requirements. Since there's no dynamic memory allocation happening and all the space usage is fixed, the overall space complexity is O1. This makes the algorithm highly efficient in terms of memory usage. Let's compare this approach to a brute force solution. In a naive method, we could simulate the elimination process by maintaining an array of numbers from 1 to n. For each round of elimination, we would remove elements from left to right, then reverse the direction and repeat until only one number remains. However, this approach would need O(n) space for the array and O(n) squared time to simulate the eliminations. Each pass through the array involves O(n) work, and with O log n rounds of elimination, the total time grows to O(n) squared. By contrast, the provided solution is exponentially faster, with a time complexity of O log n, and it uses far less memory, requiring only O(1) space. This efficiency arises from the mathematical structure of the elimination process, where having the problem size in each step naturally leads to logarithmic time complexity. The lack of dynamic memory allocation ensures constant space complexity. In summary, the provided solution is both time and space optimal, leveraging mathematical reasoning to outperform the brute force approach significantly. When tackling this problem, one of the most common mistakes is neglecting edge cases. For instance, scenarios where the input size is extremely small, such as n equals 1 or n equals 0, can easily lead to runtime errors if not handled properly. On the other hand, failing to optimize for large inputs could result in time limit exceeded errors, especially given constraints where n can go up to 100,000. Another frequent pitfall is inefficient brute force simulation. If you're directly modifying a list using operations like list.pop, repeatedly you're introducing a time complexity of O(n) squared, or worse, because each removal shifts elements. This approach simply won't scale for large values of n. Instead, you should consider optimized data structures like deques, or even better, look for a mathematical pattern. Lastly, it's crucial to handle the alternating direction of elimination correctly. Many mistakes arise from overlooking the fact that elimination alternates between left to right and right to left. For example, if you always iterate from left to right without reversing direction when required, the results will deviate from the problem's rules. Another mistake to watch out for is overcomplicating the mathematical approach. Sometimes, when deriving a recurrence relation or iterative formula, it's easy to add unnecessary complexity, which can make debugging a nightmare. Instead, focus on simplifying the logic and verifying your solution with small test cases to ensure correctness. Additionally, it's important to pay close attention to the problem constraints. For instance, recognizing that n can go up to 100,000 should immediately lead you to discard inefficient solutions like brute force simulation. Constraints and hints often point towards the optimal approach, so use them to guide your thought process and avoid wasting time on suboptimal methods. In an interview setting, recognizing patterns is absolutely key, especially for elimination problems like this one. These problems often involve some form of symmetry or periodic behavior, so analyzing smaller cases can help you uncover the underlying logic. Scalability is also critical. Interviewers are likely to test your solution with edge cases or large inputs, so you should start with a brute force solution only to validate your understanding, but transition quickly to an optimized approach. Clear communication is just as important as correctness. As you explore different solutions, explain the trade-offs between options like simulation versus a mathematical derivation. Lastly, be ready to demonstrate your debugging skills. For example, if a test case fails, you should be able to identify logical errors, such as mishandling the elimination direction or missing boundary conditions. Interviewers value both your problem-solving process and your ability to recover from mistakes. Several related problems can help you build the skills needed for this challenge. LeetCode 1823, find the winner of the circular game, involves elimination within a circular structure and often benefits from recognizing mathematical patterns. Problem 390, Elimination Game, directly aligns with this discussion, as it incorporates alternating left to right and right to left elimination, making pattern recognition a critical skill. While LeetCode 62, Unique Paths, isn't directly related, it emphasizes combinatorial thinking and efficiency, which can be useful for mathematical approaches. Finally, LeetCode 146, LRU Cache, focuses on caching but uses data structures like deques for efficiency, which parallels the optimization techniques applicable here. There are several approaches you can take for this problem, each with its own trade-offs. Starting with brute force simulation, this method is straightforward to implement but highly inefficient for large inputs, as it often runs in n squared, or worse. It's best suited for understanding the problem and verifying results on small test cases. A better alternative is optimizing with data structures like deques, which can reduce the time complexity to n. However, this requires familiarity with deque operations, making it slightly less intuitive. The most efficient approach involves recognizing mathematical patterns. This can yield solutions with time complexity as low as log n, but deriving such patterns can be challenging. For certain variations, binary representation or recursion can also provide elegant solutions. While these methods are often efficient, they may feel less intuitive at first. Ultimately, the best approach will depend on the constraints and your comfort level with different techniques. Great job! We've wrapped up the elimination game problem. We covered the brute force approach and discussed key insights about iterative elimination patterns. Thanks for watching, and don't forget to like and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!